Good morning, everybody. So today is some tough math stuff. So hopefully we're ready here. Hopefully you have a calculator. If you need to use your phone, I guess that's okay. But we got some math coming at you today. What I do like to start is the week going over the week schedule so you guys know what we're doing. Today is called Calculation Heat of Phase Change Notes. So it is a tough kind of math, and we'll quantify phase changes. Tomorrow, we're actually just going to practice that concept, and I'm going to actually give you a mini quiz at the end of the period tomorrow. However, we're going to learn it in the first half of class today, practice it today. Then I'm going to let you practice in the morning. You'll take that quiz at the end of class tomorrow, and so hopefully you'll all be prepared for that. Just because this is the last thing we have to learn, and we can't burn a whole week with nothing else before the test. Then we do have the thermochem review kind of set up on Wednesday. If you don't want to wait until Wednesday, you already have the review packet, but Wednesday is the day that we have carved out for you guys to do your review packet and ask any questions. Thursday, the people in the cohort that is here, you guys will burn food and do that lab. And then Friday is your unit test. Not quite sure what that looks like yet. Got some good ideas over the weekend of how I kind of wanted to, or if I was putting it on paper, what it would look like. Now I got to figure out how to get that into Schoology. So that's kind of where we have the big things are. Tomorrow we're going to have a quiz on this, and Friday you have your test. Okay. So kind of the biggest thing we got going on for this week. Now, wherever you're keeping your notes, this is the last entry for these unit notes. We're going to write a few things, and then we're going to do one really big math problem. Okay, so let's write this down. Thermochem notes number 5, energy associated with phase change. Energy associated with phase change. Going to get crazy. So exciting. All right, I got everybody accounted for. Are we ready? Now, the main thing that we have to do in order to teach you this, if you can think this way in your head, you're going to be fine. If you could pretend that this is like a road, okay? Here's a road, here's a road, here's a road, here's a road, and here's a road. They're all different highways, and you have to pay a toll to go on each highway. And it depends on how much mass you have, okay, and how much you have to pay a toll to do that certain thing. Because we have been talking about water, 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 water at the liquid state. But water comes in a lot of different states and can go through different phase changes, and it costs a different amount of energy, the energy associated with phase changes, okay? It takes more energy to heat up liquid water than it does solid water, and it takes a little bit different energy to heat up water in the gas state. So all of these different things. We have been living in this area with water between 0 and 100. Today, and this is an honors chem thing only, just so you know, my regulars do not even touch this. Okay, we have to talk about outside of just 0 and 100 with water. And each of these things costs a different amount. So if you can kind of think about it like this, and if you can kind of think in your head, all right, the solid warms, and then it stops to boil or to melt, and then the liquid can warm, and then it stops to boil, and then it's a gas. If you can kind of remember this graph in your head, you're going to be great, because each of these is going to take a different amount of energy, and then you add it all up at the end, okay? So it's kind of an overview of what we're going to do. So here we go. Energy associated, you just wrote that, with phase change. So 4.18 joules is wonderful for liquid water. But how about like ice or steam? So if it was me, I would make a little table in my notes, and I would say water phase, specific heat capacity. And if you don't remember, specific heat capacity is C. It's a C value. Specific heat capacity is C. So I would make myself a little chart. I'd make myself a little chart in my notes. So we're looking for the C value for different things. So there are 3 phases of water. There is solid, liquid, and gas. Solid, liquid, and gas. And you guys already know one of the 3. You guys know that the C value for liquid water is 4.18 joules per gram degree Celsius. And I'm telling you right now, on any quiz or test or assessment opportunity, I will give you this chart. So do not think that you have to memorize this. Okay, I will give you this chart because some of the two of the numbers are very close. All right. So that's if you're heating water. If I said, hey, how many joules does it take to make 100 grams of water go from 25 to 35 degrees Celsius? You'd be like, I got Q is equal to MC delta T. Let's do this. You can do the same thing if it's a solid ice cube or if it's gaseous water. It just demands a different C value. The C value for solid water is 2.06 joules per gram degree Celsius. Remember, that's our C value. And for gas, it's very close, 2.02 joules per gram degree Celsius. Okay, so what I want you to think of when you're thinking here is 2.06. If I'm ever below zero and I'm trying to warm a solid, I'm 2.06. If I'm in the liquid, 4.18. If I'm trying to heat or cool liquid water, and 2.02 is my C value if I'm talking about a gas. Okay, easy peasy with that squeezy. Let's do it. Now, the only other thing that we have a big problem with are phase changes. Okay. Now, the idea here is that you can heat and cool a solid, heat and cool a liquid, heat and cool a gas. But when I am melting or freezing, is there a temperature change? No. And if I am boiling or condensing, is there a temperature change? That flat line tells me there's no temperature change. So my question here is can I use Q is equal to MC delta T if I'm going through a phase change? Okay, that would throw a zero because there'd be no phase change. And once you put zero in something like this, well, we've wrecked everything. So there's this big idea that you can't use Q is equal to MC delta T because there's no delta T in a phase change. So that just means we need a different formula, and that's fine. So let's write this here. During a phase change, you are not going to Q is equal to MC delta T. You just can't because there is no delta T. So during a phase change, you just do Q of your phase change is equal to M and then this new thing called delta H. Delta H. Okay. M is still mass. No worries. That didn't change. You're just going to talk about this number, mass times this delta H. And delta H is just how much energy it takes to change phase. Okay, so the main idea is Q equals MC delta T works for this angled line, this angled line, and this angled line when you are in a phase and you're heating and cooling. However, when you are state changing here or here, you just take the mass times this given, okay? And there's two of them. There's one for freezing and melting and one for boiling and condensing. Let's do it. Two more things to write down. Heat of fusion. The reason why this is called heat of fusion is why you might know what a fuse is or a fuse box or a breaker box in your basement. If you're like, oh no, I blew a fuse. What does that mean? Well, you used to go to the basement and they have to stop a surge of electricity coming into your house. They would have what's called a fuse. And a fuse is a little piece of metal that if too much energy tries to go through it, that little piece of metal will melt. So if you think of fusion, another word for fusion is melting, you're good. Melting and freezing. Okay, the definition for the heat of fusion, let's write melting and freezing here. It's the energy needed to melt or freeze 1 gram of a solid at its melting point. The energy needed to melt or freeze 1 gram at its melting point. So this is your delta H for if you're melting an ice cube or if you're freezing it into water into an ice cube. Perfect. Okay. And it's just a given. I would just write, we'll talk about that in a second. I will just write delta H of fusion for H2O is 334 joules per gram degree Celsius. Again, I will give you this number on a quiz. You just have to know that fusion means to melt or freeze. So that means your ice cube takes 334 joules per gram to melt. So if you're like, hey, I have a 10-gram ice cube and it takes me 334 joules per gram, all you do is you multiply those two together to tell me how much energy it takes to melt that ice cube. It's very simple. Okay, so that is the one around the 0 degrees. Melting and freezing, we're talking 334 joules per gram to melt or freeze water. Okay, now we got to talk about this one, the one that happens around 100. Awesome. That's called the heat of vaporization, and that is vaporizing or condensing. Vaporizing or condensing. The stuffy definition, if you would like. The heat energy needed to vaporize or condense at 1 gram of a liquid at its boiling point. Heat energy needed to vaporize or condense 1 gram of a liquid at its boiling point. Okay, so this number is huge. Your delta H to vaporize water, you have to give it enough energy to make it from a liquid to go all the way to a gas, which is huge. You need 2,260 joules for every gram of water to turn from a liquid into a gas. So this takes 2,260 joules to complete per gram. Okay, so now we have a lot of different pieces. That's not the hard part. The hard part is putting it all together. Okay. All right, let's do this. Are we ready? All right, so the math problems are where it comes in to be a little bit harder because it kind of turns into a reading game. Where are we starting? Because the idea here is that I can start, I don't know, with water at room temperature and I want to boil it to be a gas at 110 degrees. How much does that cost? You would have to then calculate 1, 2, 3 different Qs. Okay, so figuring how many Qs you need is the hardest part. Let's do one of the hardest ones first, and then we can kind of go backwards from there. Okay, so on your worksheet, I would write one of these practice problems in your notes. I'm sorry, not your worksheet. In your notes, I'd write one. I'm not quite sure what we're going to do for semester exams. I think we're going to do something. It won't be a big exam. You can't have like an hour and a half test anymore. But I think we'll have a little something, so it's good to have an example in your notes. So in your notes, I would write how much energy is required, and you just might write how much energy to warm 265 grams of ice at -15 to steam at 185. And then you'll have an example of this in your notes. You'll have an example of this in your notes. How much energy required to warm 265 ice? -15 degrees, and I want to be steam at 185 degrees Celsius. So I'm going to have to show you a few examples. This is the biggest example. This is what we would call a 5Q. Okay. Remember, I told you that each of these are different roads. So in your head, if you can think about this graph, if I'm at -15.4, that means I am way -15.4 degrees Celsius. I'm way down here. And I want to be steam at 185 degrees Celsius. I have a lot of roads I need to travel. I need to warm up to 0. I need to melt. I need to warm up to 100. I need to vaporize. And and then I need to warm up to my final temperature. So the other thing you want to remember is that when you are in a phase, and you have all this stuff like right above, probably in your notes, when you're in a phase and you're changing temperature, you will do Q is equal to MC delta T. When you are changing phase and there's no temperature change, you just take your mass and multiply it by whichever one of these two you are doing. And remember, fusion is at 0, vaporization is around 100. All right, so let's talk. I like to first do what I call words. Okay, we'll do the math here in a second, but if you can write it out in words first and start the mental process, you'll be able to turn it into math, no problem. I will not require you to do the words on the quiz, but let's just talk through kind of the words here. So I, right now, am currently solid at negative 15.4 degrees. The first thing I have to do is I have to warm my solid to what temperature does it melt at? 0. So the first thing you need to do is warm your solid to 0. Okay, warm the solid to 0. So that's the first road I'm going to travel. Then I stop here. Then the next thing I need to do is I need to melt. That's going to be my next road, is I have to melt. Now I'm over here. What I am at this point is I'm liquid at 0 degrees Celsius because I have just melted. Now I need to warm my liquid to 100. Warm liquid to 100. So I'm traveling up this little road here. Now I'm on liquid water at 100. I need to stop and I need to boil or vaporize, however you want to say that. Then I'm almost to where I want to be. Now I'm steam at 100, but I want to be gas at my final temperature of 185. And there's a couple pitfalls here that students sometimes run into. Okay, so if you can think about it in words, whether or not you have to write them down or you have them in your head, you're good to go. So what we're going to do is we're going to quantify this. Each of these are a Q, Q1, Q2, Q3, Q4, Q5. We're going to figure out how much energy it takes to go on each of those little pieces of our trip. All right. Now, so I just like cluttered this thing up. Let's get out of here. So we're starting way down here at negative 15.4 degrees. It says I need to warm my solid. So if I am warming, that means I'm doing a Q is equal to MC delta T. So Q is equal to my mass is going to be 265. I am warming a solid, a solid, a solid. So I need to multiply that for my C value, 2.06. Here's one of the harder tricks on this. If I'm at negative 15.4 and I want to get to 0, how many degrees do I have to go? 15.4. Okay. Awesome. Then I'm going to stop and I'm going to melt. Now you're like, wait a second, I can't do a delta T for melting. You are right. When you are changing phase, all you do is your M times whichever one of these you're doing. So I'm going to take 265. And the one that I use for melting is 334. Okay. Now, I have traveled up and over. Now I'm right here. The next thing I need to do is warm my liquid. Now you're like, oh, this looks familiar. Warm my liquid water. I'm at 0 and I need to get to 100. So I already paid to get to 0. So now I need to pay to get to 100. So I need my MC delta T, mass, 4.18 because it's liquid. And I'm going to go another 100 degrees. Okay, perfect. So that gets me up here to be 100 degrees. I am a liquid at 100 degrees right now, but now I need to stop and boil. Oh, yeah. If I'm doing a phase change, I'm over here. Q is equal to M, 265, times, if we're boiling or condensing, we're going to do 2260. Perfect. There's one last pitfall. Will people fall into it? You're not going to fall into it because you got this. Now I'm over here. I am a gas at 100. But remember, I want to be a gas at 185. So the last thing, I'm going to do one more of these. Q is equal to MC 265 times my C value for my gas is 2.02. Last place you can mess up. We've already paid to get to 100. How many more degrees do I need to go? I only need to go 85. Very good. Okay, so people will be like, oh, let me put 185. And they're like, no, you've already paid to get there. Then all you're going to do is you're going to multiply 265, 2.02, 15.4. 265 times 334. Multiply it across. So if you don't want to write all these numbers down, I get it. So just write to yourself, mult is more an example. I can't spell multiply. Mult across. And then if these were tolls, and you're like, I had to pay $8,000 to do that, $88,000 to do that, $110,000 to do that, you would add it all up to get a final Q value. Okay, so these numbers are going to be really big. Okay, so that's how much it costs to take an ice cube out of the freezer and turn it into steam at 185 degrees. So you're paying for each step. Okay, that is like you're traveling from California all the way to New York City. That's the whole gamut that you can go. But you guys know you don't always start with ice, and it might not always go to steam. So the hard part with some of these is reading what the problem wants you to do. So after you feel comfortable with this, let's go ahead and grab that worksheet in front of you. I'm going to show you a couple hard ones, and then I'm done yapping so you guys can practice. Okay? Awesome. Worksheet in front of you. Worksheet in front of you. It says phase change, energy associated with phase change, calculation, practice number 1. Energy calculations involving phase change. Okay. Good stuff. All right. Let's get into it. So again, you're going to practice this today. We're going to practice it tomorrow. You're going to have a quiz at the end of the period. Let's do it. I like to write a few things up at the top to remind myself. This is when you are in a phase. Okay. These are my C values to remind yourself. And when I'm in a phase, I can use Q is equal to MC delta T. This is when it says phase change, changing phase. This is my delta H value. And you just do your mass times delta H. Okay. So if you have all this information, and you will have both of these things on your quiz tomorrow at the end of the period, we're ready to go. Hardest part is reading the question. Calculate the number of joules needed to turn 525 grams, I'm going to throw an M on there, of water at 100 degrees to steam at 100 degrees. So we started off with one of the trickiest ones you can get. When you think on this little chart, if you are water at 100 and you want to be gas at 100, how many roads did you take? You only took one road. You went from one side to the other side with any temperature change. Any temperature change here and now. All you have to do is take that water and vaporize it. Okay, so the blue part that I'm writing is just what you want to think in your head. You do not have to write that on the quiz. So that means I'm going to do Q is equal to M delta H. So Q is equal to M 525. Which delta H am I going to use if I'm vaporizing? The 2260. It didn't ask me to change the temperature, didn't ask me to warm it, didn't ask me to cool it. All it asked me to do was vaporize it. 1Q, 525 times 2260. Final Q. Got a lot. 1,186,500. Unit for Q is always a joules. Okay. So some people find that really easy. Some people are like, well, how did you know only to do 1Q? That's silly. So again, like I'm telling you, if you can keep this little graph in your head, or if you want to keep this graph out, you have it in your packet, slide it around. This graph is so important in your head. All right. Everybody got number one. Let's try number two. Calculate the heat energy needed to make 15 grams of ice. Oh, there's my N. It's at -50 to water at 50. So first, let's try to figure out how many Qs. I am ice at -50. That means I'm a solid. -50. I want to be liquid water at 50. Let's see how many roads I need to go. I can't melt at -50. So the first thing I have to do is I have to warm to get to 0. Warm solid to 0. Now I'm solid at 0. I need to stop and I need to melt. Okay, again, the blue is what you're thinking in your head. Eventually, if that can fall away and you can just do your Qs, you're fine. Now I'm over here. I am now liquid at 0. And I want to be liquid at 50. So now I need to warm my water to 50. Okay. Anybody have any questions with how I got there as far as the words? You just think each one of these is a different road. What road do you need to take and where do you need to go? All right, here we go. So that's going to be 3 Qs. I got to pay 3 Qs. As soon as you see the word warm or cool, because we're going to go down, so we'll do the warming. If you see warming, I know I'm MC delta T'ing. So my Q is equal to M, which is 15. I am solid, solid, solid. So I look up here, give me a 2.06. And if I am at -50 and I want to get to 0, that means I have to go 50 degrees. Good. Then I'm going to melt. There is no temperature change associated with melting, so I need a Q is equal to M delta H instead. M is 15. If I'm doing melting, melt / freeze is the top one. Boil / condense is the bottom. So I need a 334. Warm liquid to 50 because now I'm over here and I need to go from 0 to 50. That is a temperature change, my friend. So I'm back to Q is equal to MC delta T. 15, I am liquid water. So I'm looking at 4.18 and I'm looking to make that go 50 more degrees. Anybody have any issues on how I turn my words into math? Doing okay? Doing okay? All right. Then it just turns into really easy arithmetic at this point. 15 times 2.06 times 50. I think I put it right here. You're going to get a couple Qs. 1545, probably for the first one. 5010 for the second one. 3135 for the third one. These are all amounts you kind of have to pay. Add them up. 9,690 and make sure you have joules on there. Okay. I'm going to get you started with just the words on the next one, and then I want you to go kind of start to fly on your own. One thing I guess I should say here is you can also go down, calculate the heat energy released. Same thing, whether you're warming or cooling, you do the exact same process. It's just where are we driving? So calculate the heat energy released when 635 grams, oh, that's my M, of steam at 100. So be very careful. I am over here and I am gas at 100. So I'm at that flat line right over there. It's going to condense and then cool to water at 90 degrees. So the first thing I need to do is I need to travel across this line. I need to condense. Then I just need to cool to 90 degrees Celsius. So step one, it kind of tells you in the problem. Step one, condense. Step two, once you condense your liquid, I'm going to cool my liquid to 90 degrees. There is one tricky thing here. Let's see who can get it. Perfect. So the first one, I want to condense. So therefore, I know I need Q is equal to M delta H, 635 times 2260. That is my vaporizing or condensing one. Then Q2, I'm going to take MC delta T because I'm cooling. So I need a delta T in there. It is liquid, so I'm looking at 4.18. Who can tell me how many degrees I am cooling? 10. People are like, oh, put a 90 in there because it's just no, we are at 100 and we want to go down to 90. That is simply a 10 degree delta T. Okay, so we have about 10 minutes. I want you to finish this one. I want you then to read the next one. How much heat energy is needed? Oh, this is a 5Q'er from -40 to steam at 120. So that is going to require all 5 Qs. I'm coming around. This stuff is tough. We're going to practice it again, and then there's a 3-question quiz we're going to take at the end of the period. Maybe I'll make it 2. I don't know. These take quite some time, so we'll figure it out. Okay, I'm putting the jams on quietly. I'm going to come around. I also want to talk to everybody at home, so don't go anywhere. Talk to me. What can I do? Last thing before we get out of here, please, and hang around if you have a question. I can write anybody past late if you need to. I want to show you one thing, and I talked last week to the students at home. Don't leave. Wait. Okay, I have recorded myself doing every single problem. So if you have a question, please make sure that you can come in here and that you can do these problems. I have a recording of every one. If you just want the static answer key, the static answer key is there as well. But there is a living answer key. You have to do these tonight so you feel good for tomorrow, okay? We will have a 2-question quiz at the end of the period. Okay, you guys did great. That stuff is tough. Okay, but again, we have the living answer key on there. Do a couple of these. Do your lecture questions if you can, but if you can't, we'll do them first thing tomorrow. Okay, thank you guys.